further ado, let's just go into what we're going to be doing in the talk today. So I'll give you an introduction, tell you about classical null strings, then I will go on to how you quantize the system, and then I'll speak a little bit about applications, and then conclude with some of the stuff that we are doing now, and some other future directions. And of course, please feel free to stop me at any point if you have anything to ask. It would be good to have two-way conversation about this. Okay, so so let's start. So let's start off by asking why we are interested in null strings at all, what they are and why we are interested in them. So massless point-point particles move on null geodesics. World lines are null. So null strings are essentially the extended analogs of these massless point-point particles. So so the massless point particles essentially are in one extended dimensions are your tensionless strings. Okay, so these have been looked at since Scheil did this in the 1970s. And so let's just take a brief moment to pause and think about this. So the tension of the fundamental string is given by 1/2 pi alpha prime. When we take this out to now to infinity, this is essentially the point particle limit of string theory, where the string length actually shrinks to a point. This is supposed to give you classical gravity. So this is the limit back to Einstein's equations. So when you are looking at t going to 0, this is going to be the ultra high energy, ultra quantum sort of regime of gravity, when we are going to go forward and look at the quantum mechanics of the system, right? So this is the regime that we want to focus on. And these are, of interest for, as I said, maybe understanding, if you will, very quantum gravity. We will see that it's related to strings at very high temperatures and the Hagedorn phase. And there's also, links to higher spin theory. In this talk, what I will be mainly aiming to do is I will be mainly aiming to look at, point B, which are strings at very high temperatures. Okay, so in a nutshell, what do we have? So what we have is that when you are looking at the symmetries on the worldsheet, the three-dimensional Bondi-Mesmer-Sachs algebra actually replaces the usual two copies of the Virasoro algebra as symmetries on the worldsheet. So the classical strings can be obtained both intrinsically, I'll explain what I mean by this, or as a limit of the relativistic strings and superstrings. Quantum mechanically, there are a lot of new physics which appear, and there are interesting links, as I said, to strings that are near the Hagedorn phase transition. I hope to explain these things as I. Okay, so I will start off by reminding you of this old work by Isberg, Lindstrom, Sundborg, and Theodoros in 1993, and we will build on this. Okay, this is going to be, if you ILST. So if you start off with the Nambu-Goto action, then what we see is that there is a T out here which arises in front of the action, right? So if you want to take the T going to 0 limit, this might not be the best way to try and do it. So in order to do this, what we are going to do is we are going to switch to the Hamiltonian framework. So PM are our generalized momenta, and the two constraints that arise are given by this. So if you're looking at the total Hamiltonian of the system, it is going to be the sum of the canonical Hamiltonian plus the constraints. Now, It's a diffeomorphism invariant theory on the worldsheet. So HC is going to be equal to 0. And so what you're left with are these guys. So here, rho I depict the Lagrange multipliers. And so these I have in the next line, rewritten as lambda and rho. Very good. So what you can do is you can start off with this and you can integrate out the momenta to now reach an equation which I call 2 here. Okay. Okay. And now, if you were to, identify this with the usual while invariant form, then you see that G upstairs AB, upstairs alpha beta, as I write here, can be identified with this following 2×2 metric, which has a -1 and 2 rows and minus rho squared plus 4 lambda squared t squared here. So far, everything is nice and fine. So it seems that we have done well. Now you can happily, in this equation 2, you can take the tension going to 0 limit. This term will just drop off and you're left with something which looks fine, right? But this is a singular limit and that should show up somewhere. And what happens is, as you can see, that the determinant of this metric when you take t to 0 is going to go to 0. Right, so that's the signature of the fact that the metric is going to become degenerate. So what we do is we replace this degenerate metric density by V alpha, V beta, where V alphas are now vector densities. And in this formulation, this V alphas are, identified. In the t goes to 0 limit, the action now reduces to what is usually called the ISLT action, and this is given by the V alphas. So what we can do is we can start off with this action in red, that the thing that I call equation 5, and we can treat this as a starting point for tensionless strings. This need not refer to, as I said, any parent theory. You can treat this as an action of fundamental objects. So when I say that I'm going to be deriving something fundamentally or intrinsically, I mean I will start off with this action and I'll do things from this action.
Arjun, okay. if I may ask,
yes.
So
sure.
It's very nice that you have derived equation 5, but is this unique prescription? Or could one think about slightly in a different way as well about the tensionless strings?
This is sort of the most naive thing that you can do. You can, of course, you're trying to take something. If you have more terms, then you could, of course, have more involved limits where you scale something up and you scale something down, and you can still take this limit. So this is sort of the most in your face naive thing that you can do. And this is what ISLT did earlier. So the analysis that we are going to be doing is going to be based on this. You can obviously ask, is this the most general sort of action that you can write down? And the answer to that is no. But that's sort of more, there are more things that you can write down that has to be sort of consistent with this sort of the worldsheet geometry is something that will arise out here. So this is what Eric will know well. So Carolian stuff will appear on the worldsheet. So you can do more things and keep more terms there. But for this talk and for the things that we have written so far, our focus has been trying to understand this.
Arjun, can I ask a question?
Please go ahead.
So I have two questions. One is, so since you have a degenerate metric on the worldsheet, does it also mean that in the target space there is some degeneracy going on? I mean, what is it? Is it not anymore?
That's necessarily not. Yeah. So the answer to that is not necessarily true. So you are right that it could mean that there's. Of course, it's a singular limit on the worldsheet, it could mean that there is a similar singular limit on the space-time. But let me sort of, so this is, I mean, actually something very new which we are trying to do at the moment. You could think about, but let's take one step back. Let's think about just point particles, right? Even when you're looking at point particles, they have a world line, and the world line, when you're looking at massless ones, they have a null line, right? Mm-hmm. But that does not mean that those sort of point particles, massless, point particles will have to, not live in, say, flat space or something like that, right? So, I mean, what I'm saying is that at least the point of view that I'm trying to take is that these are to be thought of as, sort of, analogs of these sort of massless, point particles. So necessarily, at least, it does not seem to me that it is going to need you to have something which is degenerate in the background. But to formally, answer that question, one needs to do a one loop analysis on the string worldsheet, look at the beta function equal to 0 equations, and see what they actually give you.
But but suppose you do gauge fixing, so that you would, a static gauge would identify the worldsheet with the part of space-time. So if the worldsheet is degenerate, would it not require a certain restriction also on the target space? Otherwise, you could not identify the two-dimensional spaces.
What I'm saying is that there could be, there could be a situation where, again, the point that I'm trying to make is when you think about the massless point particles, they don't live in some space times which are other than the space times that say massive particles live on, right? So it would, if you are thinking about these sort of tensionless strings as being a sector of string theory, it would be hard to think of it living in some sort of space-time which is not the same as that.
Okay.
But it could be that if you have a fundamental formulation, as we are saying, if you write down this action, this is an action that and you just forget that it came from some string theory. If you treat it as a separate action, and if you treat these as fundamental objects, it could be that if you go to quantize this system, you might find something where these things do not, they are not, say, descendants of usual string theory. It could be, but that is something that your analysis should give you. Okay. And so far, our analysis of this action, at least, does not seem to, point in that direction. Even though we have not, as I said, we have not done this one loop beta function analysis to just put the whole thing to bed.
Okay. Okay, thanks.
So if I understand, Arjun, so you're saying that no one has looked into the world line limit of this theory yet?
World line limit.
Yeah. Because you should be able to see this. If there is a singularity, right? Yeah, you should be able to see that also in the world line limit.
What I was saying to you earlier was that you have both of these. Both of these guys, right?
Okay.
So the point is that if it's a world line theory, it would not retain a memory of this being a string. So that is maybe a sort of further subsector of this. And there have been work. There has been work. In the past where people have thought about these sort of tensionless strings as being a bunch of massless point particles that exists. Actually, these guys around 93, I mean, also had this whereby they were saying that, you look at the equations and then it seems that this is a bunch of massless, point particles. But the thing that I think that they miss, that particular analysis may have missed is the memory of this being a string. And I think that is, actually going to be extremely important for what we are going to be doing from now.
Thanks. Thank you.
Sure. Okay, good. That was good. And so this is, equation, this red action is going to be, if you wish, the starting point of stuff for this, for our null strings. Okay, so now, so we have seen that, you could start off here and you could go here and you have an action. And then what I was saying is that there is this, you could start off with the action and get to your sort of favorite thing in tensionless string theory. The question is, can you also close the square in this way? Can you take your favorite thing in usual string theory, take some limits on it and get here? So what we will see is that when we are doing the analysis for the classical version, this does hold. So the next few things will be trying to emphasize this point. Okay, so let's start off slow. So what we what we will see is that the tensionless action is again invariant under Worldsheet diffeomorphisms. So we can fix a gauge which is equivalent to the conformal gauge here. What happens in usual string theory is that after you fix the gauge, there is still some residual symmetry left over. That is this Virasoro plus Virasoro, and this is central to understanding string theory. We will see that there's a similar thing that is happening here as well. So let's do this. So when you start off, you look at Worldsheet diffeomorphisms. There's this, this induces a change in the vector density. And when we are looking at the gauge V0, or you can set the small v equal to 1 as well. So there is going to be some amount of symmetries left over, and you could see that if you choose epsilon to be of this form where f and g are some arbitrary functions of sigma, then this stays the same. So there's going to be some residual gauge symmetry for this. Okay. So what you can define is you can define the generators for this, and then expand in Fourier modes like we do, and then after doing all of that, the symmetry algebra that you're left with is the one down here. Actually you do not get any central terms. It's I've just written this central terms to show you what it could have when you're when you move away from the when you quantize the system and then have ordering ambiguities. So this is the symmetry algebra that you get, and this essentially is what is known in the literature as the three-dimensional Bondi-Mesner-Sachs algebra, or equivalently or isomorphically the 2D Galilean conformal algebra. Okay. All right, so this is going to be sorry,
Arjun, can I ask a question about the previous the BMS as well? So should we also understand this as some sort of like group contraction, the Wigner contraction of?
That's what I will do next.
Excellent, good.
Yeah. So okay, so this is going to be the central object of what we are going to be doing. So this is sort of the ideas and methods related to this algebra is going to be what we use to understand this tensionless sector of string theory. Okay, so you start off with so what is the tensionless limit from the Worldsheet? So if you look at the residual symmetry of the tensile string in the conformal gauge, these are two copies of the Virasoro algebra. Now the worldsheet is a cylinder, so it's best expressed as a conformal. So this symmetry is best expressed as conformal generators on the cylinder. So let's write ln as e to the in omega, and L bar is e to the in bar del omega bar. When you are going to take this tensionless limit, what is happening is that the length of the string becomes infinite. Okay, so it's naive. I mean, you know, hand wavingly, this is somehow sigma going to infinity. So what we are also interested in is a closed string. So this is best viewed as sigma goes to sigma, and I mean tau goes to epsilon tau, as epsilon goes to 0. So yeah, if you wish, you know, a usual, worldsheet, the string is becoming long and floppy. So it's a limit where you focus on some small, epsilon t, and sigma becomes large. So let's see how you take this limit here. So what you do is you define these flat ln's and flat mn's as linear combinations of these curly ln's and ln bars, and these new vector fields are well defined in the limit. You can just go back here and just you can just look at this, take those linear combinations, and you will see what you end up with is ln is of a form like this, and mn is of a form like this. This is exactly what the previous analysis of residual gauge symmetry also gave you. These are the exact forms. So this closes to form the three-dimensional BMS. Okay. Okay. So let's a word on what's happening on the worldsheet. So on the worldsheet, this is the limit where sigma goes to sigma and tau goes to epsilon tau. So if you're thinking in terms of velocities, it's sigma by tau is essentially going to infinity. So effectively v by c is going to infinity. So this is the worldsheet speed of light, and that goes to 0. So this is what is called a Carolian limit in the literature. So what you're going to get is you're going to get a degenerate worldsheet metric, as I showed you. So the Riemannian worldsheet structure goes on to this Carolian or ultra relativistic thing on the structures on the worldsheet.
Arjun,
yes.
Do you then also get that nothing can move on the worldsheet in the Carolian limit, because nothing can go faster than the speed of light?
It's not. It's a little more tricky to say that, right? In the sense, this is a gauge symmetry, right? This is sort of residual gauge symmetry on the worldsheet. So there are going to be features that will look. What is happening in space-time. Yeah, so there are similar things that might happen, but it's fundamentally not the same, right? So it's not that things are moving on the worldsheet. It's just in a sense, your structure where you had left movers and then you had right movers, that is sort of lost. So we will see that this is, actually happening in a very interesting way when you look at the, when you look at trying to, quantize the system. What we will find is essentially in this limit, closed strings actually go on to open strings. We will see this. So what essentially what we will try to do is that we will, just say that, these are the symmetries on the worldsheet. These are the things that I trust. And I shall build, everything from there. So instead, so that's how we will just go ahead. Okay. So that's the.
Arjun, if I may ask.
Thank you.
Yeah, sure.
So if this is the case, then my whatever I do, even my quantization would be dependent on a particular frame of reference I'm looking at, because I've lost my.
That's not true, actually.
Okay. And why is that?
So what is happening is, what do you do in string theory, right? So what you do is, in usual string theory, let's let go of the fermions. So what you do is you have a you have a simple action So you're like, you have some scalars on the worldsheet, and you quantize them. I mean, just like a free scalar, but you also impose this. So this what the residual gauge symmetry does is you impose that on on your Hilbert space, right? So that what we are going to be doing here is exactly the same thing. So we are going to look at this system in this gauge where we're going to sort of quantize things in this gauge, but we will also have to keep in mind how to impose the this sort of constraints on the Hilbert space to look at what the physical spectrum is. So it's not really, so you are if you wish, you are on the worldsheet now is a null surface. That's all. Okay, so the fact that you get this three-dimensional BMS algebra is because that the worldsheet is a null surface, and you are looking at the massless version of it, because the strings the worldsheet action is a sort of massless action. So massless plus being light just makes it this this particular algebra. So it's not a frame dependent thing at all. Okay.
Sorry, may I ask also?
Yeah, please.
Previously, you identified BMS3 as a Gaussian conformal algebra, right?
Yeah.
And now you are saying that it's actually Corellian tensionless worldsheet. So I would expect something like Corellian. Is there any relation with this, like Gaussian conformal algebra and having a Corellian tensionless?
No, it's, as you know, right, when you are in 2 dimensions, these are, both are one and the same. The algebra is the same, right? BMS3 and GCA2 are the same.
Yeah, but, oh, yes.
So I'm just saying that this thing is the algebra that appears on the worldsheet is this. That's all.
Okay.
And it's from this from what I've just shown you, the limit that we saw, the tensionless limit on the worldsheet is an ultra relativistic limit. Actually. That's all.
Yeah. Thanks.
Okay.
But may I just maybe
Sure.
in some sense Eric already asked, but just to be sure, so the target space symmetry classically are still Poincare, is that right?
We are not saying anything about that yet.
Mm-hmm.
So I've been sort of carefully trying to skirt that. So, I agree. I agree what you guys are trying to say. It's a singular limit on the worldsheet. It should point to something singular happening in space-time as well.
Mm-hmm.
But the second thing that I'm also trying to say is that if you are thinking of these strings as being, a sector of usual string theory, so it's very hard to think of it that, you take, fine, string theory and so on, and just focus on its high energy sector.
Mm-hmm.
That is going to live in something else, right? So that these are two sort of points of views which do not go well together. So what we did, this is not out yet, but we are we are all friends here. So what we tried to do is we looked at a light cone analysis, and trying to close. So suppose things are on flat space, can you close the algebra? The horrendous thing that you have to do, right? So trying to close the Poincare algebra, and what are the dimensions you get. So you will see right at the end, if you do things, if you take care of everything out of one sort of bosonic closed theory, you can get 3 separate sectors. And it so happens that all of them, so there are two sectors which work in D equal to 26, things close up, and there's one more sector that works in all D. Okay. So that's what. So it may be that this one sector which works in all D will also be sort of enabled to background sort of Carolian structures and so on. But for the other 2 sectors, things work. So I mean, even for this sector, there are no sort of extra things that you get. So it's not like your usual relativistic theory was in D equal to 26. Now I'm saying that you take some limit from there. What you end up with is a theory that only works in D equal to 7 or 8 or something like that. So even that works as a separate sector in the theory. Okay, but I agree. It may be that these are flexible enough to also admit things like ultra relativistic structures appearing in space-time. I mean, as you guys know very well, right? So these Bargman structures can fit in. So I mean, you might be able to go one dimensional higher or one lower and fit in those extra things that you guys are thinking of, right? So I'm not sure about the full picture yet, but this is the math that I have done.
Okay, thanks.
Okay, yeah, sure. Okay, this is fun. All right, so let's do some very naive sort of analysis. So the spectrum of in order to get the spectrum of the tensile thing in conformal gauge, what do? We quantize the free worldsheet theory. The worldsheet theory as a theory of free scalars. Then we have the constraints which appear from the vanishing of the equations of motion of the metric, which are essentially fixed to be flat. The physical states. So the operator form of this is that the physical states must vanish under the action of the modes of the energy momentum, T mu mu, and T and T bar, right? So let's just get this down. So that if you're looking at the energy momentum tensor of the 2D CFT on a cylinder, these are the expressions for it. You can take these ultra relativistic limits, and what I want you to focus on, are central charges right now are 0. So these are the mode expansions of it. You can do it in a more sort of intrinsic way as well, but these are the mode expansions for it. So classically what you will see, the constraints on the tensionless string are T1 equal to 0 and T2 equal to 0. I'll work this out and show you. And quantum mechanically, so this is going to be the sandwich of T1 and T2 equal to 0. I would not be able to get to this at the end, but there is a very interesting thing that happens here, and you can show that there are actually, more than one ways of trying to implement this. But that's going to be very near the end if I ever reach the end, which is looking like maybe a month from now. Okay. All right. So what do we want to do? We want to make some sanity checks and so on. This is going to be a slide which is full of formulae. So this is the equations of motion in this V alpha gauge, V0 gauge. So it's just x double dot equal to 0. So you solve this, so you get a form of the thing which goes like this. Now, what we are going to do is we're going to look at closed strings. So this A0 is going to go to 0, and we are going to be left with just this guy, and this guy's not there. So if you write down what the constraints are, you will see that you can write it in this form. So it's x dot squared equal to 0. So you just plug in what x dot is out here. So you see that it's b minus n and m plus n. And here it's a form like this. Very good. So what we're going to do is we're going to define some bilinears. This L is going to be a dot b, and these m's are going to be b dot b. So if you rewrite them, so what you will see that the constraints are of the form ln minus in tau mn, exponential I and sigma. This, if you go back to my previous slide, was exactly the expression of the t's which I showed you. As a sanity check, so this is familiar from the one which was obtained algebraically previously, and so you can look at the algebra of the modes, and you will get that AA is 0, BB is 0, but AB is not. So once you do this, now you can use this to construct what the algebra of the LNs and MNs are, and as a sort of sanity check, again you see that the BMS3 emerges from this. So everything seems to be working, everything seems to be nice and fine. This is all that you expect. So we have this mode expansion now. Okay. So I said I'm going to derive my favorite things also as a limit. So what is my favorite thing now? I want to try and derive what the solution is from the solution of the usual string. Okay. So the string mode expansion, which every one of you know and maybe love, is something here. So what you can do is, the systematic limit that I laid out to you earlier, you can just, do that systematically, and you can show that this is an expression which you get. So you just take this, plug in the thing that I've written, and then, look at this expression and look at the earlier expression which I wrote down for you here. So once you do that, you can then, identify, sorry, this has to go through all of this again. Yeah, so you can then identify A's with the alphas and also B's with the alphas. And so the equivalent thing, what we write down here is, you can write down, the quadratics of A's and B's, which give you the ln, and the quadratics of the alphas, which give you the script L's. And this again reproduces the earlier thing that we had got by just looking at at the algebra and just making sure things don't blow up. Okay, so everything seems to fit in very well. Okay, so that's what the classical thing was. So that's what so the idea is that when you're looking at the classical picture, both trying to do things intrinsically, or by looking at the equivalent thing from the string theory, they map on. They map on, and when you take care of the limit, everything works out very nicely. Now, there's a lot of fun that one can have when one tries to look at the quantum mechanical systems which arise from this. All right. So I'm going to start off with something which are called BMS Induced Representations. This, I don't know why I do not write this here. This is, let me try and rectify this. This is Oblak, Barnage, and others. Okay. So there is a very important class of BMS representations called massive modules. So the Hilbert space of these modules contains a wave function that satisfies the following property here. So these are labeled under M0 and L0, and all the MNs acting on this is equal to 0. Rest of the MNs. So notice that M pluses and M minuses both acting on it gives you 0. This defines this induced module, and here the basis vectors will be given by all of these ln's acting on the state ms. Okay, so n's can be both plus and minus. Now let's think of this as a limit from Virasoro to BMS. So you know that the highest weight states are ln script ln's and script l bar n's for n greater than 0, giving this equal to 0. L0 and L, this is not ln, this is, I'm sorry, this is L0. So these give you h and h bar. So this translates into ln plus 1 over epsilon mn acting on h bar equal to 0. So that is this guy, and this is this guy. So you see in the limit of epsilon going to 0, the things that are left is mn for n greater than 0, I mean annihilating the state, and mn for n less than 0, I mean also annihilating the state. Sorry. And there's also the identification of m with epsilon h plus h bar and s with h minus h bar. Very good. So in terms of the oscillator modes, you'd remember that m was, sorry, why doesn't this work? Okay, so maybe I will just write this. M was b into b. So let me erase this as well. So since that was the case, all of the mn's acting on the state is equal to 0. So that essentially means that all of the b's now acting here will be equal to 0. So we are interested in the vacuum module. So we will have bn acting on this. What we call the induced vacuum, that is going to be equal to 0. Okay. All right, so hold on a little bit more before we get on to more interesting things. You would notice that the algebra of A's and B's. Yeah, sure.
Let me ask. So this vacuum is, I think it's only true in the tensionless limit. Perhaps it's not the same vacuum as perhaps with the finite tension.
That is true. We will see how that is happening. Just hold on a minute. This is a little bit of, algebra things are going to get, a lot more interesting from the next slide. Okay. So just to set up something else, you would remember that the algebra of A's and B's was not harmonic oscillators. So what we do is we define some C's and C tildes to actually make this harmonic oscillator. And another important thing to note is that when we do this, these C's actually become, so these are linear combinations of creation. So you see that Cn maps to alpha n and alpha minus n. So there is a mixing of modes going on. Okay, so this beta plus minus is, root epsilon plus minus 1 over root epsilon. Now, we are also going to define a vacuum which is 0C, which is Cn and C bar, C tilde, and just the usual sort of oscillator vacuum. Okay. Okay. So this is not the same as what we were doing for the usual string theory, because it mixes up alpha and alpha minus. Okay, alpha plus and alpha minus. Now we have two things out here. Let us focus first on this induced vacuum I. Okay, so induced vacuum is defined as Bn acting on I equal to 0. In the same way, if we rewrite this in terms of the C oscillators which we have written, so this is C plus Cn plus C tilde minus n acting on I equal to 0 for all n. Okay. This is going to be important. You have to keep in mind that this is precisely the condition of a Neumann boundary state, and the solution is given by the following, this last boxed equation here. Okay. So what have we done? We have said that there is an induced representation of the BMS. And when we are looking at the vacuum of the, when we are looking at it in terms of the, oscillators A and B that we define, this becomes, Bn acting on the state equal to 0 for all n. If we are interested in the vacuum module, that just, this is what I'll be calling the induced vacuum. So all of the Bn's acting on this is going to be equal to 0. So that's point one. Point number two is I am redefining my A's and B's so as to form a harmonic oscillator basis. And in this basis, my induced vacuum is going to take this is going to be a Neumann boundary state. Okay. These are the two important pieces of information that I want you to remember. Okay. So what did I say? There was a mixing of modes, right? There was a mixing of modes in the sense these C oscillators and these alpha oscillators are mixed up, basically. So you can write the alpha oscillators in terms of the C oscillators. What is happening is that there's a Bogoliubov transformation on the worldsheet, okay? And this theta is epsilon -1 by epsilon +1, okay? So once you write down a Bogoliubov transformation between these two sets of, two sets of oscillators, the vacua are going to be related. So this is well known, and this becomes this exponential of tan hyperbolic of these guys. This theta is the same thing which is there. This is a squeezed state. So 0 alpha. So remember. So we have these alphas and we have these C's. Okay. So the 0 alpha in terms of the C's becomes a squeezed state. Okay. This is happening. And now we want to see what is going to happen, in the limit of epsilon going to 0. Okay, so this was happening at small epsilon, not necessarily epsilon going to 0. But now let's see this. So what did we have? We had two sets of modes. Alphas and C's. These are Bogoliubov transformations of one another. There is an alpha vacuum, which is the usual string theory vacuum. There's a C vacuum as well. So one of these is going to look like a squeeze state from the point of view of the other guy. Okay. Now let's try and understand what is happening. Okay. So when alpha is equal to, when epsilon is equal to 1, this so the tan hyperbolic is actually equal to 0. So this alpha vacuum and the C vacuum are one and the same. This is just a closed string vacuum. Now, as epsilon will change from 1, from the point of view of the C observer, the vacuum, this alpha vacuum, is going to evolve, and this, as we said, is a squeeze state as shown before. Okay. In the limit where epsilon goes to 0, tan hyperbolic of theta becomes -1. So what does that give you? The relation between alpha, 0 alpha and 0 C is that then given by these C's with a -1 in front of it. What has happened? If I take you back to the BMS induced representations, this is precisely the induced vacuum that I introduced to you earlier. So this is an open string. So this is a Neumann boundary state. It can thus be interpreted as an open string or a space filling D-brane. What we have done is very simply, we have then obtained an open string by taking a tensionless limit on a closed string theory. Okay, so let's try to understand what is happening in terms of pictures. So you start off with a closed tensile string, and you decrease the string tension. So the string sort of becomes long, and it's going to squeeze onto itself. It's going to squeeze onto itself, and in the extreme limit of epsilon going to 0 or the tension going to 0, this whole thing actually folds onto itself and becomes an emergent open string. Similarly, if you're thinking of it in terms of D-branes, this is what happens. So you have a closed string, which is here. This grows longer and longer and longer and longer, ultimately filling out the whole of the space-time to form a space-filling D-brane. Okay, so this is what is the decreasing string tension takes you from a closed string to this space-filling D-brane. All right, and remember what we have done is very simple. In the sense that we have just used the fact that there is this Bogoliubov transformation happening on the worldsheet, right? The new stuff, if you wish, is the fact that this happens on the worldsheet. Okay, So what used to be a worldsheet, which used to be a closed string worldsheet, has sort of now squeezed onto itself and become this, emergent open string when you take the tension going to 0. So this is this is what we have. I can sort of, excite you, or if you wish, say some more, outrageous things. So why not? So let's look at what is happening to any sort of perturbative state in the usual string theory. So we have a state psi. This has a polarization tensor xi mu nu, and we take this at level n. So we have these oscillators alpha minus n and alpha tilde minus n acting on it. Okay, so we want to understand it as the state as we near epsilon goes to 0. Okay, so very close to epsilon equal to 0, what you can do is you can approximate this 0 alpha as say this this induced vacuum plus something which is I1 into some epsilon and I squared into I2 into some epsilon squared and so on. This is an approximation. It's a little hand wavy, but let's see where this leads. Okay. Now, what we do is we are going to look at the conditions that are there for the alpha vacuum. This is simple, right? So this is alpha n acting on 0 alpha is equal to alpha tilde n acting on 0 alpha is 0 for all n greater than 0. So if you translate this here, right, what you're going to get is that for all bn, this is equal to 0, and then you're going to get some things where you relate. So you just plug back what alpha is in terms of A and B, and you can get these simple sort of relations out of this. Okay. Now suppose we start off with alpha n and alpha tilde minus n acting on 0 alpha. This state psi. Okay. Write these down, expand this out, and just plug in these guys here. Okay. What you're going to get is that this state becomes some number which depends on what n is into the induced vacuum again. So this is for any state at n, any level n. What is happening is that all perturbative closed string states condense onto this open string induced vacuum. And the idea is this. So you start off with the usual string spectrum, then this gets squeezed up, this gets squeezed up more and more, but in between there is no sort of qualitative change happening. It's just what you used to call 1 centimeter, now you call one millimeter, and so on. But what happens at the end of the day is all of those squeeze onto just one state. Okay, so if you wish, this is the way this open string forms, and all of these perturbative excitations of the closed string condense to form this open string induced vacuum. Okay, so that was what I wanted to say for the quantum mechanics. And I agree that if you're hearing this for the first time, this might appear to be sort of mumbo jumbo. But I assure you that the math that we did is very simple. Maybe you don't like what the explanations are, but I would think that it sort of forms a nice nice picture, and the math surely works out. Okay, so that's the thing that I wanted to say. And having sort of, given you a lot of things to think about, let me also try to give you a few, applications. Yeah.
I mean, so does the tachyon play any special role here, or does it just also condense into?
Yeah, it will just all just go bloop.
Okay.
So it'll just all bloop, and it will become, I mean, massless. I mean, in the limit, everything becomes
right. Okay, I see that makes sense.
massless.
And may I ask?
So
yeah. Sorry.
Yeah, it's just this naive thing, right? When you are thinking about the mass squared formula, right? So there's a 1 over alpha prime which sits there, right? So I mean, if you take, I mean, alpha prime out to infinity, or if you take, I mean, t going to 0, everything is sort of going to be trivially sort of massless. Everything is just going to be massless.
Right, but
yeah,
but in normal string theory, I mean, the tachyon means there's an instability. The theory is kind of inconsistent. But are you saying that the tensionless bosonic string does not have an instability then?
That would be a very, very bold statement to make, and I'm not making that yet, but maybe. So what we are doing. So I mean, I'll just at the end just show you guys that there's a lot of intricacy. I mean, I'm just hiding in in a lot of places, and we have not I mean, unearthed the full thing yet. I mean, we're not even close to it. But there seems to be a lot of just novel stuff happening, just because you are looking at this new algebra on the worldsheet, and its representation theory and so on and so forth. We're just building from that. So our base is that we all we know is the fact that the 2 copies of the Virasoro have been replaced with the BMS tree. Now, what does the algebra say? Just be, I mean, guided by that, and not say much more. So yeah, so that's where we are at. The induced sort of vacuum story that I told you seems to be that everything just forms a long open string. So let me try to give you more interpretations of that, if you wish. Okay, so Hagedorn physics, right? So string theory has this exponential growth of states. So the number of states at the nth level grows as exponential root n, right? So the canonical partition function of the string actually diverges at this th, which is given by this 1 over root alpha. So it's not long been looked at, and long been thought that there was a new phase and there are new degrees of freedom here. The interesting thing here is that if you are looking at the effective string tension, which is near this th, then that actually goes to 0. When the temperature approaches th, this string tension goes to 0. So our analysis is going to be useful here. So what I'm saying is that the worldsheet description doesn't break down. It just becomes something which is like this. So your Riemannian structures get replaced by these ultra-relativistic structures, and you can. So, and what is happening is, so as you would remember, when you approach th, it becomes thermodynamically favorable to form a long string as opposed to heating up a gas of strings. So the conjecture, if you wish, is that the vacuum I, this induced vacuum, is the worldsheet analog of this emergent long string, and the Bose-Einstein like condensation that is happening on this I is a signature of this Hagedorn phase transition, which is supposed to be happening in string theory. So these are new. There are new degrees of freedom which appear here. The worldsheet does not break down, but these ultra-relativistic or Carolean structures appear. Okay, so that's one. Oh, okay. I didn't actually go on to say more, but yeah. So By the way, I think I'm out of time. So how long do I have? How long do I have?
So yeah, the time is up, but if you want, we can have some discussions after your
Yeah,
talk. If you want to say something exciting, yeah, please say.
Yeah, let me take five more minutes and then just wrap this up. So this was one of the exciting things that we did in this work from a couple of years back. But we have been doing something more exciting as well. So this is a paper that appeared sometime last year, and it was published earlier this year. So the idea, I mean, this could be another whole talk, so I'm not going to go into it. So what I wanted to say is that one of the most common occurrences of Bogoliubov transformations is in the physics of accelerated observers versus say inertial observers. So this is the stuff where you replace and Minkowski spacetime and Rindler spacetime. What we did in this work is that by identifying these our Bogoliubov transformations with Rindler Bogoliubov transformations, we can recast this decrease of tension as an increase of acceleration, intrinsic worldsheet acceleration. Okay, so this in this limit, the string theory, this tensionless limit will be modeled by a series of worldsheet observers with increasing acceleration, and the null string or the tensionless string will happen when this accelerated observer hits this particular Rindler horizon, and this acceleration goes to infinity. So we have actually made this we have clarified this in this work from earlier this year, and we have a longer version of things as well, which should be out in about a month or two's time, where we work out a few more details. So that's something, if you are interested in, I would urge you to have a look at this work. And there is, again, a lot of interesting stuff happening there, something that we call a null string, complementarity, actually. So that's something which I could spend a lot of more time on, but let's not do that. And finally, what I wanted to say is that there is this. So as I was saying earlier, what can happen is from a single classical theory, you can have several inequivalent quantum mechanical theories that can emerge. So we did this and we looked at canonical quantizations of these tensionless string theories. So you'd remember that these are the classical constraints, and quantum mechanically they boil down to the sandwich thing of T1 and T2. So this amounts to, if you wish, saying that these modes ln's and mn's between physical states will be equal to 0. Now it so happens that you can have multiple ways of trying to impose this. Okay, and I will not go into the details of this. What happens is that there are 3 inequivalent vacua, and they lead to 3 inequivalent quantum mechanical theories. So I discussed what the induced vacuum was out here. There is something called the flipped vacuum that leads to the bosonic version of ambitwistor strings. And there is the oscillator vacuum, which I briefly mentioned here. This is a new vacuum, and it has the hints of an huge underlying gate symmetry. So there's a lot of new structure here that we have to explore. So that was what it was. So what did we do? So we looked at classical tensionless strings. So we produced a limiting procedure that we produced earlier work by Isborg et al. So there were mode functions that mode expansion that were done in both the fundamental and the limiting way. Things matched up well. When you're looking at the quantum tensionless strings, the BMS induced representations played an important role. the induced vacuum, appeared naturally as a Neumann boundary state, and this meant that an open string emerges from actually the condensation of all closed string modes. I briefly said that this was linked to Hagedorn physics, and this tensionless vacuum was the emergent long string near the Hagedorn temperature. And the fact, and the conjecture was essentially also that Hagedorn phase transition was linked to the, this Bose-Einstein-like condensation on the worldsheet. There are lots of things to do. So we have these three separate theories. One has to look at them and see if all of them work out in the right way. Look at this spectrum more carefully. Look at other forms of quantization. I said a little bit about the light cone. This is something that should be out in a week or two. And you could look at path integrals, BRST. One could think of if one could have some sort of quantum tunneling between these backbone. We need to understand what happens when we add supersymmetry. We understand the classical superstrings reasonably well. We can try to do what we did here for that as well. So again, we could think about superstring dualities in this regime. Do they become more intricate and so on? And this is a last slide, which, this is what some long-term goals are. We'd like to understand, if we can understand gross mandate through this, does BMS physics on the worldsheet, things like soft theorems, memory effects, do they have worldsheet analogs? We want to clear up what is happening here. This TH, can we understand the phase transitions in a clearer language? We want to maybe do this in ADS and DS. And ultimately, maybe, if you are being tremendously ambitious, maybe link up to, cosmic strings, and maybe you can think of tensionless strings in the sky and sell your stuff as being, experimentally viable and so on and so forth. I don't want to do that with you guys. So let me stop by thanking you for listening. And yeah, thanks a lot.
Thank you very much for this very exciting talk, very interesting ideas coming from various different fields, from quantum mechanics to strings. So if you have any question from the audience, please ask Arjun.
Yeah, I know the last part was a little rushed. So yeah, I wish I could have taken more time.
I have a question.
Yeah, please, Eric, go ahead.
So I was wondering, you see, often you hear people say that in some sense your limit, which leads to Carroll structures, is somehow, you could say, or maybe not the opposite of non-relativistic. But I was wondering, how much does this now compare to work on non-relativistic strings, in the sense that often what people do then is that they leave at least one approach, not always, they leave the worldsheet relativistic and they take the limit in the target space. That's what most research on non-relativistic strings is done. And I wonder, is now a similar activity in your case that could you also keep? And the reason is that because then if the worldsheet is relativistic, you can repeat all the usual string calculations with waves, etc. But is now a similar activity possible in your field, that you keep the worldsheet relativistic and you take somehow a Carroll limit in the target space, and that you get the kind of the mirror calculation of the other? Or is that
right? That is that. I'm saying that is going to be answering something else, right? So that's of course something that one would be able to do. But the point is, the question that I'm trying to ask is, what is, can we get a handle on this extremely high energy, extreme high energy phase of string theory? So if I were to do that, what I am trying to say is that, so these null strings will probe that limit. And for that, what we see, at least this way that this, ILST do it, and the way that we have been trying to do it, is that you have to make your worldsheet. You need to do things on your, on your worldsheet, right? So if this extreme high energy limit of string theory, you wouldn't, I don't know if one would expect Carolean structures to appear in space-time or not, right? So you are maybe it does in some weird way, which I do not understand. But what I'm saying is that, it seems that if you were to probe this extreme high energy sector, what you have to do is you have to replace this relativistic structures which were there on the worldsheet. That is what this analysis seems to be saying. But what what you're saying is, true. That's also a problem, of course, that one could attempt. But it's not what I am. It's not what I have been doing in this. It's not obvious. It's not obvious to me that these two are, one and the same. I would think that they are not.
But on the other hand, there are some papers where people take more similar to what you are doing, non-relativistic limits on the worldsheet.
Yes.
But that leads them often to rather exotic objects. They get funny representations. It leads to something, but it's rather exotic if you do that. The opposite of you on the worldsheet.
Interestingly enough, the work by Yele, Niels, and others, they have a limit where they actually get back this, the 2D GCA on the worldsheet, right? Mm-hmm. So that's a fun thing, because it's the same structure, right? And this is this thing that happens in two dimensions. The non-relativistic and the ultra-relativistic will be the same. So it's good. It's of interest then, just to understand what is happening, if you were to have these, non-relativistic is not like Lorentzian structures appearing on the worldsheet, right?
Yeah, you get again a degenerate structure on the worldsheet.
Yes. So again, I would, somehow, so the things that you guys were saying at first, that, once you take this singular limit on the worldsheet, shouldn't something also happen to, space-time? This is something that has been bothering me for a very long time. And, but, the thing there is what I wanted to say is that, it shouldn't be that, you take string theory and you probe a sector, and that lives in a space-time which is not the same as the the rest of the string theory. So that's one thing. It may be that you would be able to embed it in such structures, and it gives you more freedom to do that, but it would be surprising, right? If you had a sector of string theory which did not make sense in, say, flat space, right? Mm-hmm. Yeah, so that's sort of my take, and sort of this last bit, the thing that I was saying about this, light cone analysis, the thing that I just briefly mentioned. Yeah. It sort of gives you the hope that things are fine.
Okay.
So
okay.
Long answer to your short question.
No. That's okay. It's
yeah.
So Arjun, I have a question. So, first of all, it was very interesting that the coherent state we are talking about, from one vacuum to another, it becomes like a squeeze state. So actually, it is nothing but the displaced coherent state which you are getting. So and that corresponding to the displaced.
So it's a two-mode state, right?
Yeah.
One you have two. Yeah.
And the one of the interpretation which you said it already correctly, that given the fact that you have displaced coherent state, squeeze state here, you get an occupation number, and this occupation number, you are interpreting it as your Bose-Einstein condensation. So that's very good. Now, my question is, suppose and the interpretation you are giving also that all your closed string condenses into essentially space-time filling object. It could be D-brane here in this context, let's say. So suppose if I trace out all the open string end, then I would still have a interpretation of some closed string, perhaps, or not.
I'm sorry, trace out what again?
So suppose if I trace out your highly excited state.
Then
So
you do not have anything left, right?
But this is
So
what
that is the only thing which seems to be left. So the thing, let's just get back there.
In the limit when everything is becoming your space-time
Yeah.
filling.
So let's look at this one, right? So this is a closed string state at some arbitrary level n. It could be a first level, second level, or 158th level. What I'm showing you here is that state in the limit just goes to I. So whatever is left, at least the perturbative states in the spectrum, they squeeze on to just the I.
But there is also a boundary condition. I mean, my boundary condition also changed.
Condition of what?
I mean, from the say Neumann to Dirichlet boundary condition.
No, I've not done that. So this was a theory of just closed strings. To begin with, there was no sort of open string sector.
Okay.
What I'm showing you is that this state becomes this Neumann Neumann boundary state. That's all.
So then in what sense does it really become a space filling object? Then
so this guy here is just this is just a sort of Neumann boundary state in all directions, right?
Mm-hmm.
So if you have a sort of Neumann boundary state in all directions, then you can either interpret it as a closed open string which is free to move out in all dimensions, or a space filling D-brane. So it's just that. It's just the math that gives you this on your face.
Mm-hmm, mm-hmm. And what will be the tension of the D-brane then?
That's a good question, and a question that I do not have an answer to.
Okay.
And I think the devil lies in the detail of n here.
Yeah,
that is a little tricky.
So this is my question was, if I can compute this occupation number, maybe there would be a way to associate. But then there is no scale in the problem left. So that's
there is no scale in the problem left. No, there is a scale that I've introduced by hand. So I did cheat a little bit. So what I did, if I just go back all the way, you would see that in order to match dimensions, I put in something which is called a C prime. Mm-hmm. So there is it's a limit where alpha prime over C prime that goes to infinity, because it doesn't really make sense to say that a dimensional object goes to infinity, right? So this ratio is the one that goes to infinity. Mm-hmm. So if you wish my action is multiplied by something, that there's some scale in the game. But what exactly that scale is something that I do not know. It's just something that I've just put in by hand to make my life a little easier. There is a lot, there's a lot to this that I do not understand, of course. But yeah, so what I'm trying to do is that I'm just trying to say that, look, this is the thing, I trust my math, and I'm just going to go by that. So simple math. So all that we have done here is, it's not fancy or anything, right? It's just simple math, and just be a little, just be mindful that things might blow up and you take limits in the right way, and you end up with very interesting stuff.
So I have another question. So for instance, so in this tensionless limit, now suppose if I keep the tension finite, but if I introduce higher derivatives, but nothing prevents me, so I can write down essentially equation 5 in a slightly different formulation, and I can maintain all my covariance and diffeomorphism invariance and everything. Okay. Has anyone thought about from this perspective?
Why would you want to do that?
So essentially, I'm thinking that if I go into tensionless limit, I can excite all possible modes. So essentially I can have, my
Higher,
operator can become higher and higher derivative.
so higher derivatives from what point of view? The worldsheet point of view?
From the worldsheet point of view, yeah.
Higher derivatives from the worldsheet point of view. I'm not very sure what exactly you mean. You want to change the Polyakov action into something else?
Exactly.
How is that useful?
So I'm just thinking a different, slightly different formulation. Can I think about this way? Because I mean, I'm not breaking any covariance or diffeomorphism. I'm preserving diffeomorphism invariance.
If you
But
want
instead
to look at a theory of strings,
Mhm.
right? What are the extra things that you want to? So of course you can put in, I mean, things in a curved background. That's of course something that you can do, right? You can put a G mu nu there. You can put I mean, B field there, and so on and so forth. But I'm not sure about higher derivatives. Why would you want to put those in?
So, essentially, I mean, my only logic is that in principle, if I excite, my tension becomes so small that I can have, I'm putting more and more energy into my system. So in principle, nothing stops me from writing from 2 derivatives to 4 derivatives and so on and so forth. So this is my logic. Of course, I mean, I don't think anyone has looked into this way, but is there anything wrong with this?
Yeah. So I mean, I've not thought about this, so I don't have an answer to your question right away. But you are saying that somehow the decreasing string tension is going to
Means that I'm putting more and more kinetic energy into my system. So I mean, in principle, I can add more.
You're no longer thinking of it as a limiting, I mean, as a sector of string theory, but something that, when you turn, the premise is not very clear to me.
Okay.
So yeah, I mean, it's maybe that's something that one can do. So given, so yeah, so you are also not going to the zero tension sector, right? So you're somewhere in between, I guess.
Yeah, so I'm keeping the tension finite, but I'm letting
Yes.
more and more kinetic terms to be added into my system. That's what I was thinking.
I necessarily wouldn't do that, but
Why? I mean,
I mean, just
I can maintain my diffeomorphism invariance and everything. Of course, my algebra becomes more and more complicated.
It will not be a theory of strings in that way anymore, right?
I mean, yes, my action is now different than.
Yeah, it's not a theory of strings anymore. So I'm not sure why we want to do that. But yeah, I mean, of course, I mean, if it's something that, yeah, I mean, I'm not sure why the tensionless limit of string theory should be related to sort of, I mean, trying to turn these, I mean, guys on. But maybe I'm, yeah.
No,
so I've not thought about this at all. So yeah, I mean, I don't have a good answer. Yeah.
Is there
may I also ask?
Yeah.
Because I found it quite fascinating that somehow the states, the states collapse. But is there a similar story for momentum for winding states?
Good question. This is something that I would want to look at. So you see, what one thing that can happen. Sorry, I'm on a weird slide. Just give me a sec. Let's say done. Maybe we can just go there. So one of the things is that, I mean, one of the things that one could do is, so this is a sort of a Neumann boundary state, right? So maybe one I mean, there is a way that you can get, I mean, d-branes of lower dimensions as well, and so on and so forth. And then you would want to make some particular directions, I mean, compact and see what exactly is happening. That's a whole thing that has not been explored, and that is something that I would like to do for sure. And for example, there's T duality, which is there. So what happens to it here? It seems that in this limit, the distinction between open strings and closed strings, they get blurred, right? So what does T duality do? Does it just become sort of trivial? And what is happening? So we try to look at partition functions. So we have done things with partition functions for these, I mean, sort of field theories as well. So we're trying to play around with them. And it's not clear, it's not obvious at all. I mean, if there is, I mean, so these are things that, require one to sit down and just make sure that you're not trying to do things too fast. If you do things too fast, you are going to, I mean, screw it up. So here, this particular thing that I spoke on, we were stuck on this for about 2 years, and we could not make head or tail of what was happening. So, similar things are stuck in all sorts of places, but it sort of gives you, the time to go back and sort of reevaluate what T duality meant, or what winding meant, and so on and so forth. So it's nice to actually sit down and do it. But the short answer is, I don't know yet.
Okay. Because it's kind of tempting if you think at because in the mass relation for the winding, you have a 1 over prime, but you say that that's a dangerous intuition, or
afterwards, in hindsight, it is fine, but intuitions in this business can be very misleading. So that's the thing that I've learned the hard way, that you want something to work in that way, it really doesn't work. So I mean, even you try to take a limit and you think that this is okay, then you try and cross-check it in some way, then you've seen that you have not scaled something, and just, I mean, everything is simplified. So I mean, it would be good to try and figure this out more. That is for
also
sure.
the question is, what would you mean by self-dual point here? Does it really physically make any sense?
Again, I mean, my physics, I mean, sort of comes after I do the math, actually. So it may make sense. It may be that you need to scale some things up, scale some things down, and so on. But you have to do it. The math, I mean, algebra and the math. I mean, that is the thing that I say all the time, is smarter than us. So it knows what to do. We just have to figure out what it's trying to say to us. So that's the thing, essentially.
Either I introduce some fake scale, then perhaps physically I can make sense. Yeah, maybe math. So my view is opposite. Maths and algebra, they're very good, but they can also mislead the physics. So
I would think that, okay. So so my I mean, as I said, I've learned the hard way, and but yeah. So my only thing here is that I sort of force myself to go very slow on this.
No, that's
and sort of cross-check everything five times from five places before we try and do anything. But yeah, so there are lots of things to do, of course, and we just we've just scratched the surface here. And the sort of thing that at the end of the day, what I would like to say, I guess, is that we have just replaced this. I mean, two copies of the Virasoro algebra with something else. So the overarching lesson is that things that happen, the symmetry algebra is going to dictate what you do, and that's about it.
So is there any other question from the audience? If not, then let's thank Arjun again for a very engaging discussion, and we have learned a lot very interesting things from him. So
thank you very much. I hope all of this sort of goes away, and I am able to see you guys soon in person. It's been a long time. I've not been in India for this long, for a really long time. Yeah.
Okay, Arjun, thanks for the nice seminar.
Yeah, thanks.
Hopefully we see you soon.
You. Yeah, let's hope.
Okay, bye-bye.
Bye-bye.
Bye. Thank you.
Hello, खूप भालो talk.
Thank you.